From this presentation we will start the registers, and as you are in registers you must have studied the flip-flops. So what is flip-flop and for what purpose it is used? If you remember the difference between the combinational and the sequential circuits, you know that there is a difference of the memory block. We have memory block and feedback in case of sequential, whereas no memory block and feedback in case of combinational. So the first problem was to design this memory block, and if we can store a single bit data in this memory block, we can definitely design the memory block which will store multi-bit data. So the problem was to store a single bit data, and we designed flip-flop for this purpose. So flip-flop is a 1-bit memory cell. It is used to store a single bit data. It will store 0 or 1 easily. There is no problem in doing that. And if we can store 0 or 1, we can definitely store 1 0 1 1, and I will call it multi-bit data because there are 4 bits involved. So this is our prime aim in the registers. We have to design something that will store more than 1 bit. To increase the storage capacity, or I can say that increasing number of bits, we have to use group of flip-flops. This group of flip-flops is known as register. This is the most simple one-line definition for the register. It is nothing but the group of flip-flops that is used to store more than 1 bit. And the n-bit register will consist of n number of flip-flops and is capable of storing n-bit word. Very simple. One flip-flop is used to store a single bit data. In the same way, n flip-flop will store n-bit data. And if we want to design a 4-bit register, we have to use 4 flip-flops. So let's do it quickly. I am making a 4-bit register, so I have to use 4 flip-flops, and the flip-flop I'm going to use is D because I just want to store the data, no toggling and nothing else. So I just want the data to be stored, and for this D flip-flop is best. This is my first flip-flop. The input is D and the output is Q, and in the same way I will use 3 more D flip-flops, D, Q, and there will be a clock that will govern the operation, and this is my clock. Now there is one very important thing that you have to note. The clock is internally connected and applied at the same time. This clock is connected to all these 4 flip-flops internally and applied at the same time. In sequential circuit, clock pulse is not generated individually for every operation, but it is generated and given to all the operations. By this I mean, I'm not going to generate the clock for this flip-flop, then this flip-flop, then this, and then this. I'm not going to generate 4 different clocks for this flip-flops, but I will have a same clock and it is given to the different operation. So we are bound to follow the clock. We are bound to follow the clock, and this is a problem in itself. I'm going to explain why it is a problem. For example, let's take a clock with a frequency 1 megahertz. I'm having a clock with a frequency 1 megahertz. This is the frequency, and you know that the time period is equal to 1 by f seconds. So time for frequency equals to 1 megahertz is equal to 1 microsecond. So the time period is 1 microsecond, and after 1 microsecond we will have the falling edge. It is negative as triggered, so we will have the falling edge like this. These are the 2 falling edges, and the time is 1 microsecond. So after every 1 microsecond, whatever you store in this flip-flops will get changed. For example, if I want to store 1 0 1 1, then I have to simply give 1 as the input to this flip-flop and 0 as the input to this, 1 and 1 in the same way for the last 2 flip-flops. And when the next falling edge arrives, this value will get changed, that we don't want. For example, if I want to store my data for 100 microseconds, so what I have to do, because for every 1 microsecond the data is changing, our data is corrupted, we have the garbage value, what we want to store we are losing it, and if something is available forever, then we are not going to store it. What is the need to store if something is available forever? This 1011 is not going to be there forever. once we have stored this value, it will change and we don't have the same combination of bits. And for the next clock pulse, whatever be the value here is going to be stored again. So we are losing our data. For this, we have to use some independent control. And this independent control we call as load. Okay, and this load is of two types. The first one is the synchronous load, and the second one is obviously asynchronous load. For synchronous load, the flip-flop will be operational when the clock is high and also the load is high, but in case of asynchronous, only the load is high to change the value stored inside. So this is the independent control that is in our hand. When we make this load high, the data will change irrespective of the value of the clock. So what I will do, if I want to store a particular data 1011 for 100 microsecond, I'm going to make this load low for 100 microsecond. Like this is the clock, and let's say this time is 100 microsecond. So I will make my load low for this 100 microsecond. This is my load and it is low for the 100 microsecond, and there will be no change in the register. The value stored is not going to change. It will be 1011, and there will be clear input. You already know what is clear input. It will reset our flip-flops, and in this case it is going to reset all the values of the 4 flip-flops. This clear is connected inside to all these flip-flops. So this is a brief introduction about the registers, and in the next presentation we will see the data format and classification of registers. This is a very important thing that I have explained you right now, especially this load. This load is our independent control, and we don't want to lose our data for every passing clock pulse. That's why we use this load. So this is all. See you in the next presentation.